We live on the cutting edge of physics, materials science, engineering, and nanotechnology. Because at Lockheed Martin, we're engineering a better tomorrow.
My name is Mike.
I'm Mike.
I'm reading your
Jeff.
name tag. I knew those name tags were going to be a problem. All right, that's Mike. I'm Jeff. We work at the 3M company up in St. Paul in the world headquarters. And our Visiting Wizard program, normally we take science to the classroom. Okay, so we go kind of classroom by classroom, and so in the introduction you heard about we have 29 different kit topics we take out right now. And it's been very popular. Some of our plants around the country and other facilities around the world have mimicked our program. But it got to the point where a lot of schools were like, hey, you know what, we're going to do a science fair kickoff. Can you guys come in and do an assembly program? And the answer was no. Our stuff was all small, hands-on kinds of things. And so we got enough requests. A few of us kind of got together and thought, can we put something together that's maybe a little bit bigger? And so that's what you're going to see today. It's kind of going to be a little hodgepodge of some of our kits, kind of the biggest of the 3M Visiting Wizard program. Now, we need help from you guys this afternoon, right?
That's right.
It's afternoon. All right, so are you guys going to be up for that? You guys think you can help us out here? All right, well, first thing, a lot of it, we're going to get everybody involved, not just hands. We're going to get everybody involved. And so
we're going to take this line right down through the middle. Did you bring the laser?
No.
That's good, because last time we did this, we burned all those seats and we had to pay for them, so it's good.
Right, yeah.
All right, so imaginary, we're going to take everybody who's on this side of the line. You're on Team Mike.
How about some noise if you're on Team Mike?
Yeah.
All right, now guess what? Those of you that are on this side of the line, you're on Team Jeff. So come on, let's hear some noise for Team Jeff. All right. Now, what we're going to do is we're going to hold up some signs. When Mike has his sign up, Team Mike, you're going to yell whatever it says. When I have my sign up, Team Jeff, you're going to yell whatever it says. We want to fill this whole upper deck here with all kinds of noise, all right? So, are you ready, Michael?
I'm ready.
All right.
Are you ready, Team Mike? All right.
Are you ready, Team Jeff? All right. Oh, we can get louder. There we go, louder. One more. All right. There we go. Well done. Round of applause for all of you guys making lots of noise for us. Very good. All right. Enough of the yelling and screaming.
Yeah, have a drink. All right, so the great thing about it is we are going to actually do some science. I mean, Jeff and I are going to do some science, but you're going to do science too. So one of the very first things about science is scientists make careful observations. So for the next demonstration, I want you to keep a very close eye on Jeff, observe what he's doing, and find out the science.
Hey, look, there's Einstein back there.
Yeah, enough of that.
And whoever you turned your head, remember, you got to be watching me. Let's try that again. Hey, look, there's Santa Claus. Oh, much better.
Yeah.
All right, so I got 3 cups up here. I got a bottle of water. I'm going to pour water in our top cup here. So there's water in this cup. And there's not water in these 2 cups. We're going to make it easy on you. Again, we need your help on this one. So I'm going to point at a cup. You're going to yell yes or no whether there's water in that cup, all right? So here we go. All right, now that was probably a little too easy, so now we're going to make it a little more challenging, and we're going to put these 2 this way. Now, you've seen the shell game with the magician? They put the balls underneath the cups, and they ding with their magic wand, and the balls never where it's supposed to be. We're going to try to do that with these cups, but can I turn this cup over? No, because the water's going to run out, right? So we got to do it this way. So what I'm going to do is I'm going to slide the cups around. You guys are going to watch this cup here, and we'll stop a couple of times, and we'll see how you guys do. So are we ready?
All right. Here's a hint. The water is in the red cup.
All right. So are we ready? Are we ready?
All right.
Are we ready?
Yeah!
There, now we got them ready.
Go.
All right, watch the cups. Here we go. Watch the cups. Sliding the cups. All right. All right, accuracy and volume is awesome. Here we go. Let's go again. Here we go.
Be careful with that.
How long do we get to do this?
45 minutes.
All right. What do you think? One more time?
One more time.
All
They're
right,
really good at it. Now keep an eye.
Watching the cups, watching the cups, watching the cups. Oh, probably not that cup.
That's right. We know it's not that one.
All right, now I got to do it real long to confuse everybody again. All right, let's do this.
All right, here we go.
All right, do we have water in this cup? Do we have water in this cup? Therefore, the water's got to be in this cup, right? Wait a minute. You guys are right. I'm not very good at this.
Him the whole time.
The water is, in fact, still in this cup, but it's no longer a free-flowing liquid like it was. We put a powder in beforehand called sodium polyacrylate, and now it has stage fright, apparently. And what we did is we now turned that free-flowing water into now what kind of looks like a chunk of Jell-O. You got that bag again, Mike? I'm spilling powder all over.
All right, shake that off.
Probably don't want to have to clean that up later. All right. So as we understand it, this is called sodium polyacrylate, and it was discovered by a scientist at the Dow Chemical Company in Midland, Michigan. And I've read anywhere that this will grab up to 200 to 600 times its weight in water. And what's interesting is these particles all kind of stick together, so you get this nice little chunk. Now, scientists at the Dow Company are just like us at the 3M Company. We get to do really, really great science. And by the way, you know, Steve had the thing, do it big and do it oversized. What we like to say is we get to do science all day long, and we get paid for it. Okay? So that's going to be the response when we ask that question as we go during the day today, and we get paid for it, okay? And pretty well, actually. All right, so they come up with this, and now what do we do with it?
Yeah, what can we do with that? Now, this is great, but people have already invented Jell-O, and I'm not sure I can eat that.
Yeah, I don't think we would want to eat that. So it turns out the first place this was actually used is in disposable diapers, okay? The idea being that if you can get the water away from the baby's skin, the skin tends to be healthier, and when the skin's healthier, the baby is happier, mom and dad are happier, the neighbors are happier, the neighborhood is happier, and so the idea is that's what it was in there for. So kids, if you got younger brothers and sisters or cousins or somebody that are still in diapers, and ask before you do this because these diapers are a little expensive, so don't do it just without being permission first. But if you tear one open and shake it over the table, a little bit of powder will fall out, okay? It's not going to be as much as we had in the cup there, but a little bit's going to fall out, and the idea, again, is to take that water away from the baby's skin. Now, big market. 3M plays in the disposable diaper market as well, but where else can we use this? Now you're starting to see the commercials the last couple of years of seeds that have some coating on them, and what's interesting about that water there is it's not chemically reacted into that particle. It's what we call chemically adsorbed on, and so that water actually can come back out again. So in the case of agribusiness, things like that, now you water your seeds, you get that water that's hanging around by the seed, and if you're like me, you forget to water it after you plant it, the water is still there available. Hopefully the seed will germinate, and you can grow some grass. Oh, boy.
That's a lot of talking, Jeff.
Yeah, we have time for you to do something,
I think we need
Mike.
to do some more science. I'm going to need some help. You ready, buddy? You ready to help me? Come on up. All right. Okay.
Now, did you notice all the adults kind of cringed when you walked over that way?
Oh, yeah. Yeah, they were a little concerned, but not this guy. He said, all right,
we got Mr. Enthusiasm.
Come on with me up here in the front.
Nice shirt. I love the Nike shirt. Very well done.
All right. Okay, so here's a couple things to know. First of all, never turn your back on a crowd. They look friendly now, but the minute you turn your back, they'll throw popcorn at you, okay? Or hot dogs or whatever else they've got. All right, are you ready to help? Do you know why I asked you up here? No. All right, but you're still here, which is what makes you different from the adults. They're all terrified. All right, put on your safety glasses. Okay, now, are you looking cool? You feeling cool?
What do you think? Does he look good? Does he look good?
All right. All
yeah.
right. So what's your name? Tell us your name. Rylan. Okay. How are you with snakes? Bad? All right, okay, Jeff, kill the snakes.
He doesn't want the snake, huh?
Yeah.
All right, so let's reach in the bag and get rid of the snake.
We'll get rid of the snakes. There we go.
All right, snake is gone.
All right, excellent. So what else do we have in the bag?
We have 2 of these things. I'm going to give them to you.
All right, fantastic. All right, so let's look at these, and they're almost color coordinated with your outfit. So this is great. All right, so what do we got? We got a black plastic circle on the front. We got a handle, right? So grab one of these. How does that seem to you? Does it seem like there's anything that's going to be exciting about this? No, you know what? It doesn't seem exciting to start with. So grab the other one. All right, now hold them together. Stick them together. Do they stick together? No, they don't. All right,
they're the
so
same
pull them
size,
apart.
but they don't stick to each other, do they?
And now let's look at these handles. So the handles squeeze together. So go ahead. Can you squeeze that one together? Fantastic. Now grab them, stick them together. Do they stick together any better? They don't, do they? All right, so this isn't much fun, is it? All right, so you know what? We're going to need to make this a little more exciting.
We're going to sweeten the pot a little bit.
Okay.
I got a $5 bill here. You want to take that $5 bill home with you? Apparently he does.
Okay. now, it's getting more exciting now, isn't it? All right.
All right, so what we're going to do is we're going to put the $5 bill in between the plates.
Okay.
We're going to put them together. Now, all you have to do is pull it apart like you were doing before, and you can have that $5 bill. So go ahead, take that, pull it apart. Pull. Hey, it was easy before.
It's tough now, isn't it? All right, I tell you what. You grab one hand.
I'll
hold
your
the other
back
side.
Here.
There we go.
Pull
now
hard.
pull really hard.
You got $5 to take home
really,
in there. Pull
really hard.
Pull.
All right.
I think he's maxed out.
All right, here we go. You grab both hands. We're going to use gravity to help us. You were trying to do that. Are you ready? All right, here we go. Pull really hard, really hard, really hard, really hard. Oh. All right, you know, I'm sorry, buddy, but you're not going to get the $5. However, there is some science that we're going to talk about. So tell me, it was easy to get these things to come apart before. I'll give Jeff his lunch money
Mike
back.
normally keeps this, and most of the time he gets away with it because I forget.
All right, so when the handle is closed, so hold this up. When the handle is closed and when the handle is open, look at the black part. Do you see any difference in the black part? No? All right, go ahead and feel the black part. Does it feel like there's any difference? It does. Does this one feel like it's curved in a little bit, like a suction cup? Well, that's the science behind this. So when we take these two pieces and the handles are undone, and we put that $5 in between and we put them together, what's in between the pieces of black plastic along with the $5? It's the stuff that we breathe. Air, that's exactly right. So when we put those together, like this, and then we close the handles, it changes the shape and makes the shape concave like a suction cup. When we do that, we have air trapped between there, and when we increase the volume that the air is in, we actually decrease the air pressure between these orange cups, right? So we decrease the air pressure between the black pieces. The air pressure on the outside stays the same, so we have higher air pressure here, lower air pressure in between. That causes these things to be forced together. Now, the great thing about science, and one of the things that we love is when you learn science, you can apply it to life, is that it will take more than 100 pounds of force to separate these two apart. So that way, you don't weigh 100 pounds, do you? You don't. So I knew I'd be able to lift you up, and these things would stay together. You'd be safe. Jeff would get to keep his $5, but the whole thing sounds a little bit like a dirty trick, doesn't it?
Yeah.
Yeah, kind of.
Remember, his name is Mike.
That's right.
He's the one that did it to you.
But you are a great sport about this, to come up here and learn some science and help demonstrate that. So we do have some things which might even be more fun than $5. So Jeff will give you this.
We got some 3M stuff. There's some kid-friendly stuff in there. You get to keep those stellar safety glasses. And Some of the adult stuff that's around in here. Remember, Mother's Day is just around the corner, all right? So hang on to that for Mother's Day. How about a round of applause for Brian coming up to help us? So there's an example of, these little suction cups. You can hang glass with them. You can put them on pieces of glass. Again, there's pressure around us all the time, so as long as there's no leak, that thing will stay on there. Somebody discovered this, so you can also slap them on a fender if you can get them to seal. You can pull out fenders, so you get this dent removal, what do they call it, hammerless or something? Anyway, so you might be able to save yourself a lot of money by buying a $15 suction cup and pull it on your fender and going from there. But so anyway, so there's one example of, using science. We talked about the sodium polyacrylate to make some money. And, here's another one. Somebody came up with this idea a bunch of years ago. Those of you that don't sleep very well at night, you'll see infomercials about this in about 3 o'clock in the morning. And these space saver bags or vacuum saver bags, really what they are is just a big Ziploc bag. And you can put something like your pillow in there. It does come with a little tool to make sure you get a good seal. And you seal up your material inside there, and it doesn't look any different, does it?
It doesn't, so I don't understand what the big deal about this is.
Well, it says vacuum on it. Maybe we need a vacuum.
Oh, well, it's good that we brought a vacuum.
All right, so we got a Shop Vac. All right, we're going to slap the hose on one end here. So this is kind of the key to this thing, is this little attachment where we can put our hose on. All right, fire the vacuum up here. Now as we take air out of the bag, again, the pressure is going to go down inside the bag. And look what's happening to our pillow. That's probably enough. All right, does our pillow look any different? Yeah, it kind of got all flattened down, didn't it? So what we did by taking air out inside the bag, because there's air pressure outside the bag, it pushes on both sides, squashes our pillow down. And the real key to this is this one-way valve here. It lets air go that direction, but it doesn't let air go back in, and so otherwise we'd have to run the vacuum cleaner all the time. Between the noise and the energy, people aren't going to do that. So now we want to put these on a shelf in the closet. We can put a lot more on top of that shelf, but is this a very good pillow to take a nap on? No, it's kind of all squished in, right? So the idea is that then when it comes time where you actually need it, you open up the bag, you let air back in, and voila, our pillow is back exactly the same way as it was before. Now we can lay down and take our nap. So I'll be back.
All right, Jeff's going to have a nap. He'll be back for a 3 o'clock show. We'll pick this up then.
We don't have a 3 o'clock show.
Don't have.
All right, so us being scientists, so again, this works really well with sweaters, pillows, blankets, sheets, things like that. I think it'd be a very good way to store Christmas ornaments or light bulbs.
Only once.
Yeah, only ones, right, because you kind of have to have something that'll flex and rebound. Well, being scientists, we like to make measurements, and so we actually found a scale that fits inside the bag. So normally, we put the scale down on the ground, we stand on it. It's got some springs in it, and so the farther those springs move, the bigger the number it puts on the scale. So somebody like me gets on top of the scale, going to be a relatively big number. Brian gets on there, I'm guessing it probably would have been a pretty little number if we would have weighed him when he was up. All right, so we put a board on the back so air can push on both sides. Now, does it make sense if we do exactly what we just did? We take air out of the bag, air is going to push on both sides of the scale, which is going to make the springs move. Does that make sense? Yeah, so now we're going to get a measurement of how much of that is. We're not going to weigh how much weight, or we're not going to get a number on how much air weighs, but we're going to get a number on how much air pushes, what kind of force we get. All right, our scale goes from 0 to 300. Who thinks it'll be between 0 and 10? 10 and 25. 25 and 50. 50 and 100. All right, let's go big chunks. 100 and 200. 200 to 300. How about over 300? Now we see all the people that weren't listening because our scale only goes to 300. So I don't know that we're going to read above 300. So hopefully we won't, or I'll get laughed at.
Yeah. Well.
All right. So we had votes all over the place.
Okay.
But again, really feel air pressure per se, do we? So, all right, let's hold it in a spot there. We got to kind of get it in the right. You going to handle all of this, or what do you need me to do? Need me to do the on-off part?
Okay, let's see if we...
So we want to get the scale to say 0 on it first. All right.
Go.
Yep. All right, it's thinking. 300.2 pounds. The over 300 people win, and I'm done. I quit.
All right.
Awesome.
Well, this is great.
Yeah, because that can't be.
Yeah.
300 pounds pushing I don't feel 300 pounds pushing on me. That can't be right, Mike.
That's ridiculous. 300 pounds on both sides of the scale from this air. I mean, that's the size of my chest.
Right. That's why it can't possibly be right,
All
can
right.
it?
So how many of you think the scale is wrong? How many of you think the scale is right? Well,
how about when you stand out in the morning? Do you vote the same way?
Yeah. Well, it turns out, I'm sorry to disappoint, but it turns out that the scale actually is wrong.
Thank heavens.
Yeah, so 300 pounds is not anywhere close. It turns out that our Shop Vac can only take out about 10% of the air that's in this bag. So this number, 300 pounds, is off by a factor of 10.
30.
The other way.
The other way?
Yeah, so part of STEM is mathematics, right? So we only take out 10% of the air. That means the pressure on this is actually 10 times higher than what the scale reads. So instead of 300 pounds, this should read 3,000 pounds.
Wait a minute. That's like the size of your chest, like you mentioned.
That's right.
3,000 pounds is like the size of a small car.
Yeah.
If we parked the car on Mike, do you think Mike would notice that? Who wants to do that experiment?
Hey! Wait a minute, even Team Mike has turned on me.
That's right, man. Everybody always votes to do that. All right, we're not going to do that because he whined for weeks the first time we did it.
Yeah.
So, but the reason why, it turns out that number is right. You can do the math, and air pushes on us a lot. But because if I hold my hand out like this, I have air above my hand pushing down on it just about 15 pounds per square inch. But is there air underneath my hand? Yeah, and it turns out the air underneath, because air pushes in all directions, it pushes up just about 15 pounds per square inch. So it's just about 15 minus just about 15.
Just about 0.
Just about 0, yeah, depending on what the just abouts are. But anyway, so that's why we don't notice air pressure. We have air in our lungs, we have air inside of us, and so we really don't notice the air pushing around us. Now, the weather people look at real subtle changes in air pressure to help them predict the weather a little bit. Sometimes it works, sometimes it doesn't. But the idea that this air pushes around us all the time is really something that's a little hard to it's not intuitive because of the fact, now if you go swimming and go under the water, you feel pressure there, right? And so that's why when we're bathed in this fluid all the time that does it, it's just kind of a little counterintuitive that it's actually there. But we're going to actually do a couple more demonstrations to do some more things related to that.
You know, I think, Jeff, you've revealed one of the interesting principles, that some of these demonstrations work because of a difference in air pressure. There was a difference in air pressure outside of the vacuum bag compared to inside the vacuum bag. There was a difference of air pressure outside those puller plates compared to the inside in between the black parts. It's the difference in air pressure that lets us do really interesting things. Now we're ready to try something, one of my favorite parts of this demonstration show.
Yeah, this is Mike. Mike loves this demo. So we have a couple of glass blowers at 3M, and so they made us this globe because Mike's always wanted to blow up a balloon inside of something. Anybody ever tried to do that before? It can be a little bit difficult. But anyway, our glass people were able to take a big round bottom globe, put a flat side on it and a hole in it for us, and then the little neck on here. And it actually turns out Dan, who actually made this for us, is no longer with us. So thank you very much, Dan. Appreciate it. But anyway, so I'm going to hold on to this. You want this or I want that?
Yeah, you hold on to that part.
And is there anything inside the globe besides the balloon right now? Air, right? All that air's in there. All that pressure is in there. So if I hold the back of this and don't let the air come out, is Mike going to be able to blow the balloon up very far? And that's kind of what the problem is blowing a balloon up inside of something, is you got to deal with that air that tends to get trapped in there. All right, give it a go, Mike. Guy, you're not even like halfway there yet. Come on. All right. As expected, that air pressure in there kind of prohibited from blowing that balloon up, didn't it? Now.
Maybe if you parked that car on my chest,
you'd be just as winded as you are now, or you think you'd be able to do it then? All right, I'm going to let him have it so that, and I'll walk away. So now, if the air comes out the back, now it makes sense that the balloon can inflate, right? So he's going to get that all inflated, but can he take his mouth off because it's on that glass neck?
Oh, wow. I'm sorry. I didn't pay attention. Did you say not to take my mouth off?
Yeah, you were not supposed to take it off because the balloon was going to deflate when you did that.
Oh, so I have to keep inflating the balloon in order to keep it inflated.
Well, the cat's out of the bag now.
Right. So that's the one-way valve, just like we saw with those bags. So there we go. You'll hit the wait a minute.
Nope, I can see right in there. That thing's wide open.
Yeah, so there's no valve inside. It's just a normal balloon.
Wait a minute. We stretch the balloon. The molecules in the rubber are all stretched. They don't like to be like that. They want to shrink back down. So why didn't the balloon shrink back down? It does if we would have done it out here.
Well, the science associated with this, it all has to do with the difference in air pressure. So inside the balloon, we have that air pressure that's about 15 pounds per square inch. But if you paid careful attention as I inflated that balloon, I put my finger in this hole in the back and pushed it against the balloon. That allowed the air that was trapped between the balloon and the glass to escape out through the hole in the bottom of this flask. And so there's very little air between the balloon and the glass. That means the air pressure between the balloon and the glass is much less than 15 pounds per square inch. So the higher air pressure inside the balloon keeps the balloon inflated because of the difference in air pressure. And it will stay this way until we equalize the air pressure between the balloon and the glass.
Ooh, it even sounded like thunder.
Yeah, and actually it's kind of warm up here under the lights, so that was nice.
Thank God it was your breath and not mine.
So the key with this is that the difference in air pressure allows us to inflate the balloon inside the glass globe.
Because if you got more on the open side, it'll either stay open or get bigger. That's what you're saying. Got more pressure on the open side.
Yep. So if the pressure inside the balloon is greater than the pressure outside the balloon,
it'll either stay the same or get bigger.
The balloon will,
All right. So that being the case, I ought to be able to blow the balloon up from this side.
What I want you to do is to be able to inflate the balloon inside the globe from that side.
Oh, not over here.
Not over there.
All right. So you want me to make it get bigger inside the globe from this side here. All right. Let's see what we can do.
All right, so in this case, when Jeff inhales, the pressure inside the globe is less than the pressure inside the balloon inflates, but this way, Jeff cannot poke against that balloon to let the air escape, so he has to keep inhaling the whole time, which is why I'm talking really fast, because if I talk too slowly, Jeff passes out.
All right, and that's he hits me in the stomach to let me know he's done. So
it's the Pillsbury Doughboy thing.
All right, so that's all static air pressure. Air pressure, just air hanging on top of us, pushing down on us, gives us some things that we can try to do. Now, what do you think if we start to move the air? Who thinks the pressure will go up? Who thinks the pressure will go down? Do you want to vote over again if I tell you there's no way you can get that wrong based on how I ask the question? Okay? So the way I ask the question, do you think the pressure will go up or go down? Both answers are right. So who thinks the pressure will go up?
All right.
Who thinks the pressure will go down? All right, we got a better split that time.
Yeah. So how many of you were here for Steve Spangler's show? So he started the show with a great demonstration of air pressure and teaching kids how to TP
the
houses. So I'm not sure we want to do that. But so we're going to talk a little bit about similar science. There we go. Hey, you need to roll that back up. Take it back to the Marriott. All right. So if I blow on this sheet of paper, the air pressure goes up in my breath and it pushes the paper up. Now, Steve brought out that roll of toilet paper and he blew over the top of it.
And so you can't do it with a regular sheet of paper at school on Monday and amaze all your friends who didn't come to the festival this weekend. rather than steal the toilet paper out of the bathroom.
Yeah, which might not be a great idea. You never know when you may need it. All right. So when I blow across the top of the sheet of paper, inside my breath the pressure is high, but around my breath the pressure actually decreases. The difference between the low air pressure over the sheet and the higher air pressure under here pushes the paper up. So this was, we talked about making observations of science. About 400 years ago, a scientist named Daniel Bernoulli made an observation, and what he found was that this change in pressure is related to the speed of the fluid. So the faster I blow, the greater the difference in pressure, and that's why, go ahead and blow on that sheet of toilet paper. That's why when Jeff blows slowly, the sheet of toilet paper, moves up a little bit, but not very far.
Isn't this sort of how airplanes work?
It is sort of how airplanes work, and Steve gave us a great tip-off with this when he brought out his leaf blower, which can move air faster than Jeff can blow. But first, before we get to talking about Bernoulli, there's a time to do some real-life science. We're going to give you science that you can use at home, and here's a life lesson for all of you folks out there.
So nothing says science like these two things, right? Okay, we're kind of glad both have been invented, aren't we? Now, those of you that are here with kids, make sure you have Toilet 101 at home when they're going to start to stay home by themselves, because you don't want to get the phone call I got at work one afternoon from my oldest daughter, sheer terror in her voice, "Dad, the toilet's overflowing and I can't get it to stop." Okay, at least show them how to turn the water off. You can fix everything else from that at home. So the idea, we're going to do a little Toilet 101 here, and the idea is that a toilet is basically, everybody's got their own little water tower in the house, right? When you flush the toilet, the water goes down, and then you hear it go psh afterwards, and what it's doing is filling up that tank behind you while you're sitting there, so that, again, when the next time you push the flush handle, valve will open up, water goes into the bowl, and if there's not too much of this in there, it goes out down the hole in either the septic or the sewer, somewhere where it's not in the house. We don't really care where it goes, right? But now if you use too much of this, then sometimes gravity isn't enough to get it to move it along, and then we have to go to Exhibit B, right? Thank God somebody invented this thing, right? Because before this thing, we used this thing, okay? Ish, right? Yeah, so anyway, thankfully somebody came up with this idea. Now, if you start to plunge and you're plunging and you don't seem to be getting anywhere, don't call Roto-Rooter right away. Make sure you don't have a bubble under here. Okay, because if you got a bubble under here, gases are reasonably easy to compress, and all you're going to be doing is making that bubble get bigger and smaller as you're pushing, and you're not going to be pushing where this is. Okay? Tip it up, get a big bloop, then start to push on the water. Hopefully the fluid will push. It's much harder to compress. Pushes down where this is stuck. Gravity starts to work again. We're all back to where we were. Going after Steve is always a problem anyway, but, we work at a multi-billion-dollar company, and we got this roll of toilet paper, and Steve had this great big thing that said something about the Marriott. I don't know what that meant. But
Steve got to stay at the Marriott, and our corporate controls make us stay at the Holiday Inn Express.
So anyway, Bernoulli, again, this air going over an airplane wing is what provides lift for an airplane for it to work, and airplanes fly every day, all day long, right?
Yeah.
And so obviously it works, and good thing I'm not blowing out there on the wing to get that thing off the ground, because we wouldn't be going very far.
Thing. And actually, it's Bernoulli's principle that says the greater the speed, the greater the difference in pressure. So if we want to raise a commercial jetliner, we're going to have a big difference in air pressure from the air pressure above the wing to the air pressure below the wing, so that there's much less air pressure above the wing, so the air pressure below the wing will lift the plane up in the air. So that means it has to move a lot faster than you can blow.
Yeah, way faster.
Yeah.
Do we know how fast?
Well, actually, because of the advent of the internet, another great technology advance, we can go to a website and we can look up, like the Boeing 737, a great commercial airplane. In fact, may have been the plane that we flew in on to get here. It says, according to the Boeing website, the 737 has to go 175 miles an hour before it will generate enough lift to be able to leave the ground.
All right, so the airplane goes up in the air. Do we ever have to stop at a stop sign when we're on an airplane? No, because what happens if the airplane stops moving? We're not having air go over the wing anymore, right? And then we don't have air going over the wing, we can't turn gravity off. Gravity's going to be on, and airplanes tend to come down when we do that. So we're going to reinforce what Steve did. We're going to do exactly what he did. We're going to bring out a Shop Vac that can go blow a little harder than I can.
No, we're not going to use a Shop Vac. We're going to use a blower.
Leaf blower,
Leaf
right.
blower, yep.
All right, and we're going to...
All right, put on your safety gear.
All right, I can do that.
Okay.
Man, I should put these on when I sleep.
You should.
All right, so we're going to go a little bit faster, and those of you here that were earlier today found out that, in fact, going a little bit faster does make a big difference, doesn't it? Except I sound funny when I talk with those on. All right, so yeah, there's your souvenir for today. Go ahead and take that home.
Yeah.
It hasn't been used yet, so I don't know if you want to roll it up on that. You can actually use it when you get home. But anyway, as we saw before, when we get that fast-moving air, we get a lot more lift, and so this idea that we can fly an airplane seems to be a little bit more obvious, and obviously, again, it works day in, day out.
Yeah, but so that demonstration you've seen before, but there is another interesting demonstration we can do with the Bernoulli Principle, which actually seems to be a little more fun.
All right.
So let's start out.
Back to our Shop Vac.
Let's go back to our Shop Vac.
You gonna do it? You want me to do it?
Here you go. You're steady.
All right.
All right.
All right. So we're gonna turn on our stream of air. So now we've switched the hose, so now air is blowing out. So it sounded like thunder again.
Yeah, the sound guys love that.
Yeah. All right. So if I put the ball in the stream of air and let go, are we doing magic or are we doing science?
That's right.
All right. I hope they said science.
Yeah, it's science.
All right. So somebody might say, "Wait a minute, Jeff. Well, you got some force going up, which is our air coming out of the hose, and we got a force coming down, which is gravity. And so that ball is just going to find that spot where force up equals force down, and truly that's where it's going to sit. But notice that it's shifting back and forth. It's trying to fall out of that stream, but the high-pressure air around that airstream is actually acting like a bunch of hands and pushing it back into the center. I'm going to have Mike turn this off and see if I can catch it. Ooh, thankfully you did that before I was ready.
Exactly.
And because it was science, it didn't matter, because as long as air is coming out of the tube, that ball should get pushed to the middle. The only problem is every once in a while we get that little flick and it'll hit the edge, and then we lose it there. Now, do you think we can turn the air on right here and start it from sitting on the hose? And the answer would be?
Yes.
Yes, yeah, we can. All right, so let's get rid of that one.
Okay.
How about the bigger ball? You think we can do the bigger ball? All right.
All right.
Get that out.
Ready?
Hey, by the way, I never did find the snake.
Yeah, the snake went back.
What kind of snake was that?
Yeah, it'll be on a plane later, so it won't be a problem.
All right.
Okay,
all right,
ready?
So go ahead, give me some. And we'll throw this one up in there.
Okay.
And it turns out the beach ball being lighter now does in fact float higher, because where we get that force up equal the force down is a little bit higher in this airstream. But notice that the ball doesn't spin. I mean, the amount of air going around all sides of that ball is completely uniform. Every once in a while you get a little bit of a twist, but that's like the world's greatest knuckleball right there if we were playing baseball. Now, we've had this ball for a long time, so it's very well trained, and so we actually can make this now go over towards Mike a little bit. Mike can use his magical wizard powers and call the ball over. Yeah. Now, are we doing magic or are we still doing science? Science, yeah, we're still doing science. But now you get to see that ball is literally trapped in that low pressure in the faster moving airstream, because now gravity's coming down. Our air is going off at about a 45-degree angle or so. Now, we'll see how slow we can do this. Eventually, gravity does win this race. The ball gets out far enough in slow enough air. And it's not being pulled back down by gravity to come back to the airstream. And eventually we do get it to actually float in there. But again, there's another way of showing the Bernoulli principle. instead of throwing toilet paper all, oh really, I said you could have that. That's perfectly fine. Rather than throwing toilet paper all over, that one's a little less messy where we play with the balls instead. So
fantastic. All right, so Jeff, I think now is a great time where we can talk a little bit. We talked about some science. We did a little inkling of math. Maybe we ought to talk a little bit about some engineering.
Engineering, okay, that's right. It is the engineering is the E word in STEM, right? Yeah. And it's baseball season, so we brought our Louisville Slugger stuff. All right, so what we're going to do here, raise your hand if you know what an engineer does. And not the guy that drives a train engineer. Okay, so we got a lot of hands up. That's good. That's probably not unexpected at the festival here that people would know what an engineer does, but scientists kind of discover the laws of science, the laws of physics, the laws of chemistry, those kinds of things. And what the engineers do, the engineers take that and then make something useful out of it, okay? So like a bridge, rather than have to swim across the river or go way around a lake or something, now we can build a bridge, go over the top. And so they take all of these science principles and come up with something useful. So what we're going to do here, everybody will watch my hands. You're getting very sleepy. Very sleepy. Okay? We're going to invent the leaf blower, okay? We're going to kind of go through the scenario what we thought maybe happened when the leaf blower was invented. Obviously, they've been around for a while, lots of times, and so more than likely we figure it kind of started like this. The leaves fall down in the fall. Fall is football season, right? And back where we live, we get snow most of the winter. And so if you leave the leaves on the ground and you let the snow come down on top of it, you got a real problem come springtime because your grass is going to be really slow to start. Got all kinds of bad things. So you got to get that leaves up off the ground when they do fall down. So we envision Mr. Engineer sitting on TV on a Sunday afternoon watching football, and his wife comes in and says, "Look out the window, dude. We got leaves out there. They're kind of scheduling snow on Tuesday. We probably should do something about it." And so Mr. Engineer goes, great football game, but she's right. I better get out there and move these things. And raking is just the pits. It's those of you that have to do it, I hate it. So the worst thing about owning a house for me is having to rake. That wasn't enough to get me to invent a leaf blower. But anyway, you look out the window and the wind blows, and it's like, hey, look, the leaves move when the wind blows a little bit. All I got to do is get the wind to blow all the leaves in my neighbor's yard, and I'm off the hook, right? Yeah. Now, can we control the wind? Not very easily, right? Sometimes, they might blow in your neighbor's yard on Sunday, but then come Monday, they all, plus his, come back into your yard, so they maybe isn't going to work. But I remember, hey, I got this Shop Vac that if I put the hose on the backside, it blows air. Hold up that sheet of paper. It blows air. Now, maybe I can take this out and move the leaves that way rather than have to use my rake. Okay, and obviously it's going to move things along. Now the problem is this isn't very ergonomic, is it? Okay, we got this thing on one side, plus you need a long cord probably can't really tell where you're blowing, so Mr. Engineer goes off to the plumbing store. I don't know if Steve knows what aisle these are in at Home Depot.
Yeah.
All right, so now I can put this piece on here. And now maybe a little easier, a little more ergonomic on my hand here. Hold up our leaf over there, Mike, see if we still can move air enough to, we got air going over there. So now I sort of know a little bit better where I'm at, but we're kind of back heavy here. So maybe we need a tube on the front. That almost even looks like it blows better with the tube on it.
It does work better. You can see where you're going.
Still wants to tilt back. So we can save that problem by, first of all, not putting the first tube in too far.
Yep.
And put a little bit heavier one on. Now our center of gravity goes more that way. We, in fact, are still blowing air. So, hey, maybe we got something here. The neighbors might think I'm crazy going out and doing this, but they kind of think that already. Now, raise your hand if you know what a patent is. Okay, got a lot of hands up. Good. So what a patent is a patent's a legal document with a country that allows you to make something. So now that you go out there, you try your leaf blower, you can say, geez, you know, this is something, maybe I should try to go get a patent. Now, a big company like ours, we have patent attorneys that work for us. And so you would go in and talk to these people and say, you know, it's got to be novel, it's got to be non-obvious to be able to get a patent. So you would talk to somebody and say, what do you think? And the guy says, well, man, all you did is took a shop vac and went to the plumbing store, put some plumbing pieces on it. Not really sure that that's all that novel, but then we can come back and talk about Bernoulli again because our handle is open. Okay? Because our handle is open, when we have that air going through, or the high pressure air going through here, more air is coming out here than came in here because some's going to get pulled up in through here from the Bernoulli Principle. And the guy might say, the Bernoulli what? And I said, well, watch, I can show you. If I turn my gun on here, take a deflated balloon, put it up in the stream here, I can shoot Mike with my deflated balloon. Yeah. So you can see that air did come in through the handle, got shot out over there. And so then the guy says, hey, maybe we got something here. Let's go write it up and we'll try some things. And now the first thing you're probably going to do is you're probably going to have a lot of people try this. You're going to have them sign a confidentiality agreement so that they can try your idea, because if you come up with something that's really good but it's got a major flaw, somebody else is going to come right behind you with having solved that flaw and maybe going to start selling more leaf blowers. And so you would take this out and have people try it, and of course everybody would hate this part. You know, that's why they got the motor right on top of the leaf blower, is that it's basically right there with you. You can either run it with gas, run it with whatever. And so we want to find out the things that people like about it. We also want to find out, maybe more importantly, the things people don't like about it. Our patent guy comes back, he goes, yeah, I think we're good to go. I think we want to try to sell this. So then we're going to go to marketing. Okay, going to make it look better, right? Doesn't really affect anything, so we're still blowing our, I'm going to move over here a little bit. We're still blowing our leaves. And so now the idea is sometimes you get some serendipity with an experiment too. So, you know, maybe you're outside blowing your leaves around, and up in our neighborhood, sometimes you could get some kind of a critter to show up over there. And it turns out if we throw a, hey, get closer, you big chicken bear. All right, we can throw a magazine of ping pong balls in here, and we can actually get those to shoot off a little bit. Now we're going to do that again, but we're going to have Mike come up here and grab a net. Don't worry about the ping pong balls, we'll get them later. Yeah. So we're going to shoot another magazine of these, but rather than have you guys looking at where they're going, we're going to actually shoot them into the net here. And so what we want you to watch is that as we turn this on, we're going to get that high stream of air come through here, which is going to reduce the pressure and going to pluck up one of the balls into the chamber. Once that happens, the ball's plugging it, so then the pressure goes up backwards. You'll get some back pressure till that ball comes out. Once the ball comes out, now the pressure goes down. We're going to pick up another ball. And so watch this tube of balls go up and down as we change the pressure. All right, can you make it? All right, so here we go. Okay, so each time only one ball got plucked into the stream here because of the fact that once a ball got in there, the pressure went up, shot these balls back down, and then we can actually go through and pluck around with that. So again, kind of how we envisioned maybe how a leaf blower was invented, had a little bit fun of doing a little hunting of the grizzly bear at the same time, and I need your strength to get that stuff apart.
All right. So how much time do we have left?
We have like 12 minutes, it looks like.
We have 12 minutes?
Yep.
All right. You know what?
I think we got time for them.
We got time for these?
Or no, we want to do the other thing for sure, don't we?
Yeah, I think we want to do the other two.
Let's do the other two. I agree.
All right. So good. So it's time for more help, right?
All right. So those other two people over here that Mike talked to, come on up.
You two.
Two of you that we parked ahead of time. Yeah, come on up. Watch your step on the stairs. Come on up, come up, go in front of the table, go in front of the table, and we'll get you all suited up.
All right.
All right, and again, like Mike said, always face your audience.
Yeah.
Become a lot more famous that way. Got some safety glasses for my gang?
I do, right here.
All right, very good, very good. What side am I supposed to be on? All right, there's a pair for you. There's one pair for you.
All right.
Styling.
Okay, put your arms out, separate a little bit. There you go, good, good, good. All right, step back the other side, excellent. All right, so we're gonna do some science you can do at home. Okay, have you ever seen one of these before? Excellent. All right, I want you to hold it like this, grab it up at the top.
All right, everybody paying attention because this is critical. You got to hold it
Put
by
your
the
arms
zipper
straight
or
out.
higher.
All right, now
Okay.
I want you to start over here. I'm gonna hand it to you. You're gonna grab it. You are gonna spin.
And you're going to
gonna
hand it to
grab
the
it
next
from
guy,
him.
so you're going to grab it
Grab it up
from
at
the
the top, just like that.
There you go.
And you're gonna spin.
Going to grab it up at the top only. There you go. You're going to spin, give it to, now you're going to give it to me, but I know what's going to happen. I don't want it, so you're going to turn around, go back the other way. There we go. There we go. Hey, did we bring any applications
spin
with us?
around.
These guys got this figured out right away.
And now we want to see how fast we can go.
All right, so yeah, here we go. We're going to go
Really
fast.
really
faster,
fast.
faster, faster. I don't want to get it out of here. Faster, 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 faster.
Fast, fast, go, go, go.
This is exciting, isn't it?
Yeah, except Jeff, this bag is flopping around a lot.
So do
All right,
we need to
fast.
do some engineering again?
Yeah, so we need to put something in that bag to hold it
All
down.
right, so stop for a second. You're going to hold this for me. We're going to open it up. All right, so hold on to both sides. I'm going to just take, again, some regular water. All right. That looks like that enough, you think? All right, now you're not allergic to water, are you? Any other guys allergic to water?
Nope.
How about the front row?
Okay.
All right, so seal this up. All right, now let's see how fast we can go. Now that's a little heavier. Go, 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 go. Fast, fast, fast.
All right.
There we go.
I know what's going to happen next. Send it back.
All right, faster, 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 faster. It's all about productivity in the United States now. Here we go. Go, go, go. Fast, fast, fast.
All right, you hold on to this. You know, Jeff got to add something to it, and now I feel left out. And this doesn't seem quite as much fun as it could be, does it? All right, so you hold that bag open, just like that. Perfect. All right, so Jeff got a chance to do that, and we brought a little something special. And all right, so I'm going to reach in here and see what we've got, and somebody saw the previews already, because it is dry ice, right? So I got a little cup of dry ice. Okay, so does that look like ice? More or less, right? Except it doesn't drip. Okay. And that's the great thing about dry ice. It's solid carbon dioxide. Now, Steve brought out liquid nitrogen, 320 degrees below 0 Fahrenheit. Dry ice isn't quite that cold. It's only about 109 degrees below 0 Fahrenheit. And the other great thing about dry ice is that it changes directly from a solid to a gas. So, can you see it change to a gas right in front of your eyes? Yeah, see, it's not very exciting, is it? And that's the thing about it. We can't really see gases. But if we take the dry ice and we put it inside the bag, now can you see the change from a solid to a gas? You can see the bubbles, right? And it creates a little fog on top of the bag, which is kind of cool. And if I add a few more pieces, and then seal this back up. Okay, go ahead and grab it at the top. All right, go ahead, pass it
Now
off.
you don't want to be holding on to this because the change in volume is about 700 times when it goes from a solid. Hear the music back there as it turns from a solid to a gas.
Right.
So now you don't want to be holding that bomb.
We know how.
Bomb's not a right word. That bag when it pops. God, get it out of here. Other side.
Oh! All right. So we had a little excitement there, and the carpet is wet. All right. So.
Wow, that went fast.
Yeah, that did go fast. All right.
All right. So first of all you get to keep the safety glasses. The loser of the science game is really the winner of the science game. So there's some more 3M stuff for you. How about a round of applause for all these guys coming up to help us?
Right.
Why don't you guys all exit over that way?
You can go back to your chairs.
Slide over that way. There we go. Yep. Thank you for coming up and helping us.
Okay. Hey. All right. One more?
We haven't done any trash can stuff yet.
We haven't done any trash can stuff. So let's bring out a trash can. So just a normal trash can, except it's got a piece of plastic on one side. It's got a hole cut in the bottom. This is actually Jeff's trash can that I borrowed from his house. if you're going to cut a hole in the bottom of the trash can, don't use yours. Find your neighbor's trash can.
Yeah, that's right.
All right. So the great thing about this is that now we can, this is called an air cannon.
Now, if I take a gob of air and throw it to you, can you guys catch it? Yeah,
Okay.
you might as well say you did because there's no way to know, right? And so the clever people say, yeah, right here. Okay, but with this thing, we actually literally can throw some balls of air because you'll notice people will flinch as some air comes out of there because Mike's banging on the backside. That's causing a pressure wave to come through here, which is shoving air to come out the front of this thing. And it's really interesting that this air packet stays together for a considerable distance.
Right.
So,
and now it's hard to see the air. So instead, we're going to do a little more science, and nothing says exciting science like explosions or flames or those other sorts of things.
why do I always have to do this part?
Well, I guess you drew the short stick, right?
Apparently I didn't do it the last time because the helmet needs adjusting.
Okay.
Probably down a bit. Right there. I felt it. Don't knock the bottom out. Now you're too low.
Yeah, and it's
We're not going to get a standing ovation at the end at this rate, Mike.
No, this is loosening up. All right, there we go.
But again, the problem is we can't see the air. So, because that doesn't have a laser sight on it, Mike doesn't really, he kind of has to aim it up the best he can. And so we thought it would be really neat if there'd be a way to actually see air. And so what did we decide on? It was a way that we could see air out of this thing.
Well, we brought something to color the air, right? So we brought a fog machine. So we'll be able to color the air.
All right. That probably enough, huh?
Okay.
All right, so now can we actually see what comes out? Now notice it's actually a donut. It's not a flat disc. It's actually got some thickness to it. And so you can see it gets out of the bright lights and it gets a little hard to see, but it's going halfway back to the back of the sound table back there before it finally disperses its way around. All right, now, raise your hand if you played with Play-Doh before. Should get lots of hands up. Okay, so when we use Play-Doh and we have a round hole and we push the Play-Doh out, what shape is it?
Okay.
What shape is it when we go through a round hole? Now if we take and put the square end on it, what do we get? We get a square end out, right? So we decided this is going to be 3M's next big product. It's going to be called the Air Dough machine. And so might be a little copyright issue with that name, but anyway, so what we're going to do is now we're going to put the square end on. And we're going to do an experiment to see if, in fact, do we get a square donut to come out like we do with Play-Doh. So what do you think? Raise your hand if you think it's going to be square. Who thinks it's going to be some other shape? Raise your hand. All right, we got votes on both sides. It's always good. Ah, Mike, you're supposed to be making a square. It's a mini one.
Yeah, mini donuts.
All right. Now, if you had noticed when this first comes out, the reason why Play-Doh stay a square is because Play-Doh is real viscous. It takes a lot of energy to move it. Air moves really, really quick. Back up, guys. Back up, guys. Hit it harder so that they go. But what happens is when it comes through here, again, most of the air is still coming through the center, but notice that it wobbles a little bit when it first comes up, and then eventually it gets back into that donut shape or sphere shape. Sphere is a low energy state, and so it's going to naturally go back to that because of the fact it's just not thick enough for us to actually get it to stay a square. It takes too much energy to do that.
All right.
So how about if we do this? If it wants to be a round sphere to come out, what happens if we put 3 of them in there?
All right, 50 seconds.
50 seconds, all right.
All right, are you ready for 3?
Now we think if we could spread them out, we could get 3, but what's happening is all 3 of those are so close together, they're mixing, and you notice that every once in a while when we're not hitting air coming from the other direction, we do actually get even a bigger wobbly donut to come out of there. And then likewise, if we go to the big open hole, we'll get a bigger one as well. All right, with that, we're going to give up the stage. Thank you very much for your attention. Enjoy the festival today and tomorrow if you're coming both days.